Hello again, Richard Venditti here, and we're going to talk today about flotation deinking. It's the second alternative to washing. So in removing of ink, we have washing and we also have flotation. We talked about washing before, and now let's talk about the alternative. Let's start off with a definition. Flotation deinking. It's a process in which contaminants, typically ink, are preferentially removed from a pulp stock by attachment to air bubbles. Okay? And here's a nice picture that I got out of Secondary Fibers, the textbook by Tappy Press. And you can see that here's an air bubble, and in this nice photo what we see is that we've got these ink particles and they are attached to the air bubble. And the reason why is because they want to get out of the water system. They're hydrophobic. And so they'd rather be in air, they'd rather contact the air than the water. So they attach to these air bubbles, and these air bubbles are what carries this ink away from the fibers and floats them out of the system. So just as a little background, flotation, in 1992, about 80% of the deinking plants in the U.S. Use flotation. So that's a significant amount. Flotation technology has been borrowed from first, it was used in the mineral industries to separate ores, and we've borrowed it. The first flotation cell designs for pulp and paper were in the 1950s, and there's been a very steady improvement in the technology and the design of flotation cells from the 1950s up till now. And the other thing we should just mention is that de-inked pulp is a relatively new kind of technology. What I mean to say is that prior to 1970s, mid-1970s, the amount of de-inked pulp that was produced was not very much. But in the 70s and 80s, we had a huge growth in de-inked pulp production. And now in the 90s and currently, we're still trying to grow our recycling of these de-inked pulp products. We're trying to increase our recycling of office waste and publication and printing and writing grades. Okay, just to get started, this picture right here is a very old technology, 1960s technology, but it has all the parts of the flotation cell that so that we can kind of introduce ourselves to it. What you see here is there's a gray stock, so that's going to be our feed pulp. And then also what we do is we introduce some air into there. So this number 1 right here tells us that the air bubbles in the low consistency stock are introduced together. And then 2 right here, this number 2, shows us here what we're looking at is there's a rotating paddle, and that rotating paddle mixes the air bubble and the stock. Okay? And the concept here is that we're trying to get the air bubbles and the ink particles to contact. So we're trying to increase their probability of contact as much as we possibly can by some good mixing. All right, then number 3. Let me locate number 3. Here's number 3. So what happens here is that the stock, the fibers, travel towards an exit of the flotation cell. So here's our exit for our accepts. And for the air bubbles now, and hopefully those air bubbles have attached to them ink particles, those will rise up to the surface. So they rise up to the surface here. And then 5, the foam, the dirty foam, and if you looked at the top of a flotation cell, you wouldn't see bright white foam, you would hopefully see gray or dark foam. That dark foam is coming off here, it's called a froth, and it's being rejected out one side, out of number 5. And then the accepted pulp is separate, comes down this way and goes out the accepts port. And so we're starting off with our dirty pulp, and then we're ending up with a clean pulp and a foam or a froth that's concentrated with the ink particles. Okay, now for flotation to be successful, a number of sub-processes must occur. And I'll read those off and then we'll do a little simulation. First, the ink must be free from the fibers. Key point, ink needs to be detached from the fibers for this to work. The ink must collide with an air bubble. All right, so we need to have enough air in there, and we need to have good mixing. We have to have an opportunity for the ink to collide with the air bubble. And then there needs to be a strong attachment between the ink and the air bubble. So the air bubbles needs to hold on to that ink and not drop it. The ink bubble must rise to the surface. So we need to get that ink air bubble joint object needs to get to the foam and be rejected. The ink dash bubble must be incorporated into the foam, and then the foam must be removed from the system. Okay? And you know, if you've ever played with bubbles and foams, that foams can fall apart, and that's not what we want. So we want a semi-stable foam that we can have has enough strength that we can scrape off. Now we'll run a little simulation here and just kind of show you some of those sub-mechanisms. So here we have a pulp sample, and here these things here are the best we could do to make fibers. So these are little pictures of fibers. And we'll have some black ink particles and some light blue air bubbles, and we'll see what has to happen. So there are the air bubbles, there's an ink particle, the attachment occurs, it floats to the top, and then it's scraped off. So you see that there's a probability of attachment, and then the successful lifting to the foam, and then the foam needs to be stable and scraped off one more time. So there we go, and we've got to get an attachment, carry it up to the top, scraped off the foam. So what you see is that flotation can be a somewhat, it's a sophisticated process where several sub-mechanisms have to work, but when they do work, they work very nicely. We can get good ink removal and a very low yield loss. And that I would have to say that's one of the main advantages of flotation, that it's got typically a lower yield loss than washing. And another one is that the water usage, fresh water usage, is lower. What determines the flotation efficiency? So we know there's all these sub-mechanisms, but we can kind of analyze flotation by looking at contaminant characteristics, bubble characteristics, and process conditions. So we'll go ahead and we'll talk about all those right now. First question we could ask, let's talk about contaminant characteristics. Given two types of particles, which one will attach and be removed by an air bubble? Well, how do we answer that question? And I've listed some of the answers to it. Hydrophobicity is the first thing that we can talk about. And then detachment from fibers is another critical one. These two are very, very important. And then size, shape, and density of the contaminant particle are also important. So first thing we should just discuss is hydrophobic. Hydrophobicity. Hydrophobic means lacking affinity for water. In other words, hydrophobic materials are water-hating. Hydrophilic materials have a strong affinity for water. They like water, so they have strong affinity for water. So a hydrophobic material suspended in water has a greater tendency to contact and adhere to air bubbles due to its lack of affinity to water. This causes a preferential separation of hydrophobic material in a flotation process. So if you think about it, what are the two objects that we're trying to separate? The first object is the fibers, and the fibers are hydrophilic. So they're relatively happy being in the water. Now you might say to yourself, well, aren't fibers sized so that they're hydrophobic? They are to some extent. The ink and toners that we're trying to remove, though, are much more hydrophobic. And of course, they don't want to be in water. So they will, if they contact an air bubble, there's a good chance that there will be an attachment, and then that attachment will be successful in removing the ink. Just a little picture to just kind of help you understand hydrophilic and hydrophobic. If we take a water drop and we put that water drop on a hydrophilic surface, let's say a cellulose film, that water drop will look like this, okay? And this angle right here, the angle from here to here, you see it's acute. That angle right there, the angle through the water, if it's acute like that, that means that we have a hydrophilic surface. If we take that same water drop in air and drop it on a hydrophobic surface, let's say this surface is a waxed car, for instance, and that wax is hydrophobic, then that water will ball up, okay? And if we measure the angle through the water, what we'll do is we'll measure the angle from this line right here that I'm drawing all the way through the water to this surface. We get an obtuse angle. And that obtuse angle, the angle greater than 90 degrees, indicates that we have a non-wetting situation or that this surface is hydrophobic. Okay? Now, this system's a little different than the air bubbles in water with toner, but you can also, like at home, if you would, just try and draw an air bubble in water and then put a toner particle or ink particle intersecting that water-air interface, and kind of you should try to show yourself how that angle could be acute or obtuse. All right, so we know that the contaminants have to be hydrophobic. That's one requirement for removal. The second requirement for removal is that the contaminants have to be detached from fibers. And there's been a lot of research done on this at NC State and University of Maine, and it's clearly shown that the detachment from fibers has to be effective, because without that we don't get good flotation efficiency. So in typical cases, we've got three situations here. The first one is what's been referred to at University of Maine. They call it a hairy particle or hairy toner. And this toner actually is the way it's printed is you've got small solid toner particles, and they're actually melted onto the surface of the fiber, of the paper. And what happens is if that toner melts and penetrates, or there's a fiber sticking up, somehow you can get these fibers in this melted but then solidified printed area. Okay, so we have these huge fibers kind of stuck onto our ink particle. Now what happens is that air bubble is going, when it approaches this toner particle, it's going to see these fibers, and these fibers are going to act as a resistance from the air bubble, making intimate contact with the toner particle. That's one case. Another case is you have a large fiber and you have a small ink particle, but that ink particle has not been separated from the surface of the fiber. Now, there's very low likelihood that an air bubble will come and it will contact this ink particle and lift this whole fiber out. It's more likely that this fiber is going to be in between the ink particle and the air bubble and prevent the air bubble from lifting the particle there. So for ink that has not been detached from fiber like this, we have a very low chance of removing it from our system. All right, and then the worst case scenario, I hate to see this, but it can happen, is when, if we look here now, I've drawn the fiber wall, a small part of the fiber wall, and what we have is the pigment of the ink particle, and this is usually a small size pigment. But somehow, in this case, worst case scenario, the pigment has penetrated into the fiber wall. It's now inside the fiber wall, and now the air bubble really has little to no chance of getting contacting this ink particle and removing this. So it would have to remove the entire fiber, which is not the objective of a flotation deinking cell. So we can have all three of these cases, and you might ask yourself, well, what can we do about this? The most beneficial thing is to make sure that we're doing a very good job at pulping. So if you refer back to our pulping lecture, we could remind ourselves that if we use high consistency pulping with a lot of rubbing, maybe a little bit of elevated temperature, and maybe some surfactant to help liberate the ink from the fiber surface, those are all ways of improving detachment from fibers, which is a necessary requirement for deinking flotation. Okay, now the other thing that we can talk about is the contaminant characteristics of size. And if ink is too small or too large, we may have a problem in removing it in flotation deinking. So I've got a little simulation that describes that. Okay, so here in our simulation we've got an air bubble, and if the air is traveling upward due to buoyancy, then we'll have the air coming this way, and what's resisting the flow of that air are the fluid flow. And what we do is we usually draw streamlines to kind of represent what a packet of fluid, where it might be traveling as this bubble goes past it. So we have our streamlines here, and you see that the water has to, of course, when the air bubble comes up, it has to go to the side and around it when the air bubble is traveling up. And what we have here is we've got our model contaminant particle. So we've got a little black ink speck, and of course that's going to be in the water suspension, and it's going to, if the air bubble is going to travel near it, it's going to be impacted by these streamlines. So if we play the animation here, what can happen is for very small particles, what we notice is that, I'll run it again, for very small particles, that ink particle has low mass and low momentum. And so what happens is that ink particle is getting swept with this streamlines, okay? And so very small particles aren't even going to come close to attaching to the air bubbles. They'll go around the air bubble with the streamline and not be attached, okay? So it's been observed that, or stated that for industrial settings, flotation works best for contaminant sizes around 20 to 50 microns. Any particle smaller than that, or the flotation efficiency of particles smaller than that is going to be lower. And this is one of the reasons why. Because there's not enough mass or momentum for that particle to contact that air bubble. It will just go along with the fluid forces and travel along the fluid stream. So that's a very small ink particle. Okay? Now particles with larger mass, like the one shown in this picture, are going to behave differently. So this is a particle in the range of 20 to 150 microns. And if I run that animation, we've got an ink particle. Now because it's got a bigger mass, what you notice is that ink particle crosses fluid streamlines. So there's enough momentum or mass in that ink particle so they can cross over those streamlines and become attached to that ink particle. Bubble, excuse me. And there you see that it's crossing streamlines, it's actually contacting that air bubble, and we've got a relatively effective attachment. Now the last case is when we have a very large ink particle. So we're saying that this one's greater than 150 microns. All right, so we've got a large ink particle with large mass. Because of its mass and its momentum, it can cross streamlines, but we'll see what happens on this one. So here comes the air bubble. The ink particle contacts it, that's fine. But then the air bubble continues to travel up, and it was detached from the ink particle. Now you think about it, the large ink particle is going to be affected by gravitational forces and fluid forces. Those streamlines are going to try and scrape off that ink particle. And so what we can see is that very large ink particles are not effectively carried up with the air bubble. They become detached and there's no efficient attachment. And so for that reason, flotation doesn't work with extremely large contaminant particles. What can we do about this? I worked at one recycle mill where, yes, indeed, I look at the flotation cell in large specks would not be removed very effectively from flotation. One of the reasons was because sometimes they were hairy. Other times could have been something like this. So that recycle mill used kneading, a way to break large particles and then send it back through another flotation cell, and the efficiency would increase. All right, now just as another thing, I would like to talk a little bit about the foam. The foam is necessary so that we can scrape off the ink from the air bubbles, and we need a somewhat stable foam to get rid of the ink. Historically, for old newsprint deinking mills, salts of fatty acids, so fatty acids like stearic acid, were used as the foaming agent. And what would happen also was calcium ions would be added. The calcium actually precipitates some of the fatty acids, and it makes an agglomerate. And actually those agglomerates collect fine ink particles. And so what would happen is the fine ink particles that might not have attached to the air bubbles, when they agglomerated onto this calcium precipitate of the surfactant, they'd form larger agglomerates that were more likely to be separated in the process. So that was one technology. And the OMG, the old magazine, was usually added to improve the flotation efficiency. So the OMG was added to add inorganic material, ash, from the coating and the fillers, and that would help in the agglomerate formation. In the agglomerates, okay, the last comment is that the agglomerates, because of their larger size, are removed at a higher efficiency than the small newsprint inks. That was some older technology, and now for like mixed office waste and some newsprint mills, they're switching over to non-ionic and ionic surfactants, synthetic collectors. You also hear the word dysplectors because they can be used to disperse inks in washing and also collect the inks in flotation and foam. And they don't require calcium, and calcium is a cause of hardness and deposits in a mill. And then also there's lower dosages needed, so that's also an advantage to the synthetic collectors. What's that? Okay, now the bubble characteristics are also important, and the size of the bubble is the first one that we can talk about. If the bubble is too small, then the buoyancy force may not be large enough to carry the particle and bubble up to the surface. So we need to have some volume of air of low density to actually make an effective transport of the particle to the surface. If the bubble's too small, the bubbles tend to adhere to fibers. So even though fibers are hydrophilic, bubbles will attach to fibers if they're small enough. And if a lot of little air bubbles attach to fibers, then the fibers will be floated out. A dissolved air flotation cell works with very, very small bubbles that attach to almost all solids in the system, and that's an example of why if bubbles are too small, they'll attach to fibers. What happens if bubbles are too large? Then the area of the bubble surface is actually small. So if you consider having a whole bunch of small little bubbles and only one big bubble, both with the same volume, you'd rather have all the little small bubbles because they have higher surface area. And so the more bubble surface area, the higher probability that an ink particle will attach to it. Okay, another thing, if the bubbles are too large, then the volume of the bubble is huge, and then the bubbles tend to rise rapidly. Okay, and we want the bubbles to stay with the stock and have as much opportunities for contact with the contaminants as possible. If they rise too quickly, then their retention time, the bubble retention time, is too short, and our deinking efficiency will be low. Finally, the large, fast rising bubbles may disrupt the flow patterns in the flotation cell, causing channeling of bubbles. So if you have a very large bubble, what can happen is that very large bubble goes up, and then it causes a path, it separates all the fibers in that little channel, and then more air bubbles will channel up through that one channel in our flotation cell. And if you have just air bubbles just floating up in this one line going straight up, then all these other areas in our flotation cell aren't seeing air bubbles. So this channeling of large bubbles can be an issue. And the other thing about large air bubbles is that the fact that what can happen is those large air bubbles cause burping. And if you have a big air bubble like that, and that air bubble travels very high, quickly up, and it hits the surface of the foam, then the foam can start flying all over the place, and that's called burping, and that's not a good thing either. So The next thing we can talk about with the bubble characteristics is the quantity of bubbles. Increased number of bubbles have, the more bubbles we can put in there that are effective, the higher the probability of contacting a contaminant. So more bubbles is good, okay, if we can actually use those bubbles in a good way. However, if we have too many bubbles, we can have the agglomeration of bubbles into large bubbles, and then we have the problems that we discussed, channeling and burping, and that's an issue. So equipment designers, one of their objectives is how can we get the most bubbles in there but avoid channeling and agglomeration of those air bubbles. So we'll look at some equipment and see how people have done that. And so air to stock ratio depends on the equipment, and it can be 0.3 to 1 air to stock ratio, or as high as 10 to 1 air to stock ratio. And you can see the more air in there, the more chances we have to attach the ink to the bubbles. All right, the next things that we can talk about that affect flotation efficiency are some of the process conditions, how we're operating our flotation cell. The consistency is a very important one. Okay, we usually do flotation at less than 1% consistency, so we need to dilute the material. But what happens is if the consistency is too high, then the fibers tend to act as a trap, and they knock off the ink particles, and they don't allow the bubbles to mix well. So you get poor mixing, and you get knocking off of the ink from the bubbles. So the other thing is that the air bubbles, if they're trapped underneath a higher consistency flock of fibers, the air bubble can lift up those fibers much like let's call it a hot air balloon, and those fibers will have excessive fibers in our foam, which is not good. So low consistency is important because it allows the ink and the air bubbles to attach, and then low consistency also prevents a lot of fibers from getting into the foam. All right. Foam generation is also a very important aspect. We're going to add a foaming agent like we talked about, either the collector or the synthetic collector or displector. Too much foam causes too much fiber loss. So if we have too much foam, a lot of fiber in there, we'll have too much fiber loss. Too little foam or an unstable foam will allow the contaminants to fall back into the stock and not be removed. That's not a good thing. And then the amount of foam is usually controlled by the flow rate of foaming agent. It also has a lot to do with how much air we put in. So we need to kind of control the foam so that we get adequate removal of the ink, but not too low a yield of fibers. Okay, now actual feed flow rate is another process condition that's important. Too high a feed flow rate will cause very large turbulent forces, high velocity fluid, and that can cause the inks to detach from the bubbles. So we don't want too high a flow rate. And then the other thing is that the high flow rates can disturb the foam. So actually, if we have lots of turbulence, we can break up the foam. That's a problem. And then you know, we're always higher flow rates are important to us because we have production rates that usually we want to maximize if we're making a profit on our product. So we want to maximize our production rate, but we want to curtail high flow rates because of some of the turbulence that occurs in the Deinking cell. Now, flow rate also has something to do with retention time, and retention time is important. Retention time just kind of is the characteristic time that a ink or fiber particle will spend in a flotation cell. And the higher the retention time, the more opportunities that ink particle has to attach to the air bubble. So we'd like to have higher retention time. So one of the ways to increase the retention time is to actually put flotation cells in series or baffle a flotation cell so that it looks like several flotation cells in series, and that will increase the retention time. We talked already about quality and quantity of air bubbles, another important process condition. And then the waste paper furnish can also impact the performance of a flotation deinking cell. When we were flotating newsprint, like I said, old magazine was added usually at around 20%. It still is. And the filler and the fines from the magazine would collect the ink particles and also add calcium to our system and enhance flotation. Oh, and I'll go back. The other thing I just mentioned is that sometimes fillers and other chemicals in our recovered paper can act as defoaming agents. They can break the foam. So sometimes there's an issue with how much foam is being generated in our system, and it could be because of some types of oils or inks or ash that occurs in our recovered paper, and that comes through our system, and then boom, we're not getting the right foam that we had before, so we have to watch that also. All right, next thing I want to talk about is some of the flotation equipment. We're going to look at some of the designs and kind of see how these flotation cells are designed such that it maximizes flotation efficiency. Here's a first example, a flotation cell. It's black Clausen flotator. And this flotation cell right here, we've got a feed that comes in here, down here at the bottom on the left. And that feed comes down in here. And then it goes past these two turbines. Okay, so these are rotating rods. They have little paddles, I believe. And what happens is we force air close by these turbines. And then the air actually breaks off these turbines, these fast spinning turbines, and we get our air bubble. And what happens here is that our pulp comes up to the top here, and then there's a baffle right here that you can see. And then the pulp kind of spins around and it goes down again around a baffle and it goes into the second port. In the same time, the foam rises to the top, we have a scraper, and the foam is scraped off down to the bottom. Well, when the pulp from that first baffled section comes back down here, more air is added, it comes up again, and then foam is taken off, and then the good pulp comes back down here to this third baffled section, and then finally it goes up again, and then we've got our accepts right here, and then our foam is also scraped off here. So you can see that we have three baffled areas. What is that going to do for us? Well, it's going to allow us to add more air than we would if we added all the air in the beginning. So we're distributing the air a little bit more evenly across the entire flotation cell, which is good. It's going to cause those air bubbles less likely to agglomerate. And we're adding more retention time and more probability of collision between ink and fibers. All right, in this process right here, the Voith-Sulzer flotation machine, and this is one of the latest designs here. This has evolved over many years, but basically this is the most prominent type of flotation unit with over 200 installations, and that was in the early 1990s. There's probably more now. But this works with a similar principle. Here we've got a feed. It comes in through here, and that feed is split into three, I believe it's three sections. Yeah, three sections here. So we've got three inputs. And what happens is that the stock comes in through here, and then there's a little aspirator. Basically, if you have a high velocity stock, because of Bernoulli's equation, you're going to have a lower pressure, and then that's going to naturally suck air from outside this channel. So there's a little nozzle here that allows the air to come in. That air gets mixed up with the pulp, and then the pulp is introduced right here. The foam floats to the top. The overflow of the foam goes over this dam into this area right here, and then the foam is rejected. The relatively cleaner stock, again, actually goes to the bottom here, and it's pulled out this pump number one. And then pump number one, its job, it takes it and it puts it back into the flotation cell. Now there's a baffle here, so we've got a second section, so it's baffled just like that other flotation cell I showed you. Again, it's split three times to kind of add three places to introduce more air. And then the same process occurs. The foam goes over the side, and then the good pulp is taken out the bottom with pump two, reintroduced, and the same process occurs again. The good pulp comes out pump number three, and then reintroduced. So you see that we've got four actual sets of flotation. So this is like 4 flotation cells in series. And also we've split up the feed flow to each section to allow more air to be introduced. And because we have 4 sections, we're allowing more air to be introduced. So we're trying to avoid the channeling and the burping, but we're trying to add as much air as possible. And we're getting multiple chances for the air and the ink particles to attach. So it's a nice little piece of equipment, and with more than 200 installations, you can see that people are happy with it. This is a picture of the system. If you take a look, this is probably foaming agent right here. This is about 6 feet, so if I stood up, I would stand up just to about the top of these little pumps right here. And actually, this is one flotation cell down here, and here's a secondary flotation cell down here. So it's 2 sets of these flotation cells, one on top of another, done for space, to save space. Let's run this video. And this just kind of shows you the flotation cells. Now I don't think there's too much on this video, so I think we'll just escape here. Okay, so now we'll go to the next slide. Now this is a next, this actually just kind of shows you what's going on. These are all those pumps that I mentioned that are taking the pulp out and putting them back in. And let's run this video and see if we see what's going on. Yeah, actually we're watching some lines. So here the pulp is going in, and then here the pulp is coming out. It's going to this pump right here. Here's our motor. And then that pump is pushing the pulp back into the second section. Here's our 1, 2, 3 entrance. And then the pulp is coming out here. That pulp's going through here into this pump. And then that's going to be loaded into the next section. So we just kind of trace some lines there. Yep. Okay. All right, and then the next slide I'll show you. This is actually the foam portion. So this is actually the overflow of the foam. If we were on the top of the flotation cell, there's little windows to look in. And here's all that foam, and you can see that that foam is not white. It's very grayish dark. This is an ONP mill where we're de-inking old newsprint and old magazine. And I'll run this. Actually, at this mill, there was they had too much foam, and the foam level shouldn't be that high. And I'll be there in just a second. Okay, so I will run the video. And here just kind of shows you what the foam looks like. It's bubbling. Actually, right around here, this is kind of a shower that kind of dilutes the foam, knocks it down. And what you see is the foam level is above that shower. So in this case, we were having way too much foam. But you can see that the foam's traveling in this direction, and then it's actually falling down and being taken away from the system. But you can see it's pretty impressive. Here, we just have too much foam. That shower is trying to work, but it's just causing somewhat of a mess. We are doing a good job of de-inking. It's just that we've got a little foam issue right there at that point. Okay. All right. So that was a very popular type of flotation cell. Here's another flotation cell, and actually this is one that I've seen firsthand work. And this is called a Mort fiber prep flotation cell, and basically there's several design concepts here that, again, try to introduce a lot of air into the system without giving this burping or channeling. All right, so we start off down here. What we have is actually there's a 3 concentric cylinders. This first one right here actually is going to be hollow, and it's actually, there's nothing inside there. And then you've got this second cylinder, and then you've got a third cylinder right here. Okay. Now, what happens here is this is our inlet feed, so we've got a pump, and that pump is actually going to push the fluid into this second cylinder, and it's going to cause the pulp stock to rotate, all right, around the hollow cylinder. Right here is what's called a primary injector. Okay, and basically what's happening is that when we pump this stock through, again, what's going to happen is because this fluid has high velocity, this injector right here is basically an aspirator. So what happens is the high velocity stock has low pressure and will naturally aspirate or suck in air into the pulp stock. It'll get mixed in there, and then it'll be shot into this cylinder. Now, this diagram just shows one primary injector, but actually these injectors are located all the way around the outside of this, this one cylinder right here. So there might be, I don't know, 25 of these injectors, okay, and each one is taking air in. So you see that because we've separated the feed into 25 separate feeds, and we're injecting air into each of these individual feeds, we're putting a lot of air in there, and we're trying to avoid all that air being agglomerated and burping out the top. Okay, so then that's where the fiber starts in here. Now what happens is you've got this little weir here, or a baffle. Okay, it's a cylindrical baffle, and what happens is the pulp floats around, and it comes over this baffle, and it actually comes out this primary accepted stock. So we're going to just allow that pulp to come over here. The air bubbles will rise up to the surface. We'll talk about that later. But then the pulp's going to come out here, and then it's going to go to this pump. Now this pump actually is going to take the pulp. It'll come up to here, and then we've got, again, a set of secondary injectors. Again, there might be 20 of these things. I'm not sure of the exact count, but there's more than 10. And then the same thing here. We've split up this flow, and we're going to reintroduce it back into the system. So here's a second chance to add air. All right, and then the pulp is actually going to flow again like this. All right, and so we've had 2 chances to add air bubbles to our stock. We've separated it by multiple injectors here and multiple injectors here. Again, the foam continues upward, and then the good stock actually is going to also go upward, but then it's going to go, it's going to actually go up through here, and then out into this outer cylinder right here. And then this will be our accepted stock. So our accepted stock could go further on forward into the process, or our accepted stock, actually, we're going to have some more injectors. And these injectors are going to be thrown in the, back into the system. So it's a third opportunity to get more air and do more flotation. Now the other thing is that we've got these froth collectors. They look like long shoes, and they're actually attached to vacuum, and they're going to directly suck off the foam off the top. So a nice thing about this is that we can adjust the height of these things, and then the vacuum actually is going to act to suck off the material rather than scraper blades that might not be as effective. So that's one of the design considerations for this flotation cell. Okay, another flotation cell that's been used is a Beloit PDM. So it's pressurized deinking module is what PDM stands for. And this thing, the first thing you'll notice is that there's no open to atmosphere at all. It's pressurized. So what we do here is we feed our pulp, we add air all at the start, and that's called the aeration zone. And then there's a little bit of baffling here, or some baffles to mix up the air and the pulp stock. And so this is called our mixing zone, which of course is important for flotation. And then we've got our bubble separation here. So our bubbles are going to float to the top, and our pulp stock will stay at the bottom. Now at the end, we've got our foam separation section, and we're going to have off the intermediate bottom, we're going to take off the accepts. There will be a valve, so we can control how much accepts we take. And then there will be a valve here, and that will take the rejects and some air. And so the unique thing about this is that we've got these two valves, and this is the only place where we have this valving situation where we can throttle the amount of foam that we take. Here's a picture of a deinking module in a mill, and these are pretty big. I would say 15 feet in diameter, so I would stand up about this high, and this might be 30 feet long. Okay, and here, this pipe right here is the foam rejects, and here's the accepts, and this right here is our feed. Let me go back. One of the purported advantages of this pressurized cell is that because it's pressurized, there's more soluble air in the system, and that allows for smaller air bubbles and perhaps a better removal of ink. Okay, just kind of as a review, major parameters impacting flotation efficiency. What you notice is that the flotation process is a little bit more complicated than washing. We've got a lot of considerations. It's a very elegant way of separating ink from fiber, but we've got a lot of considerations. So we can think about the particle characteristics, the number, the size, the shape, the density, the surface chemistry, if they've agglomerated or not, all have an impact on flotation efficiency. And then the bubbles. Type of gas is usually not an issue. It's usually just air. But the number, the size, the surface chemistry, and the nature, whether it's dispersed or dissolved, what size it is important. So we've got the bubble considerations. And then also the process conditions. What kind of recovered paper? The type and the amount of ink in that paper. The ash content, the fiber characteristics. Is it very long, or the fibers, or there are a lot of fines? What's the hydrophobicity or the hydrophilicity of the fibers? Consistency in the flotation cell is important. Remember that if we have too high consistency, then we don't get good mixing, and the fibers can knock the ink off the air bubbles. Temperature can be an issue. Retention time is always an issue. Higher retention time, the better we get flotation efficiency. Cell design is important. Do we have too much turbulence in our system? Do the air bubbles, can we introduce a lot of air bubbles but not have them agglomerate? pH can be a factor. Chemical environment, how much surfactant's in there? What's the foam characteristics? Is it strong enough to take the ink and keep it separated from the stock? All right, and then just a last slide. Washing versus flotation. Let's just kind of look at both of these. Good deinking mills nowadays might have both. So it's not a question of one or the other, it could be both. But typically flotation uses less water and washing uses more water. And so let's go over these. Chemistry sensitive. I would have to say that flotation is much more sensitive to chemistry. So washing is a little bit simpler process. Well, all we need to do is add some kind of dispersant and disperse our ink in the water phase. Water use, we use a little bit lower flotation than washing. Okay, and but for washing, if we do good clarification, reuse our water, we can be in good shape. In flotation, we also have to get down to low consistency, less than 1%. So if you can combine that with other low consistency operations like cleaning or screening, perhaps the water use might not be as much of an issue. Yield. Flotation usually has a higher yield than does washing. And the basic reason is that flotation, we can retain a lot of our small particles. Small fines and filler can be retained in flotation. However, in washing, we're going to lose a lot of ash, a lot of filler, a lot of fines. So for that reason, the washing has lower yield. Okay? Ash removal. Flotation, we're not going to remove a lot of ash. In washing, yes, we are, just like I said before. Tensile strength. Flotation is going to be lower. Washing is going to be higher. Why is that? Well, it's because we're removing a lot of ash in our flotation. In our washing, ash actually causes our tensile strength to go down. So if we keep the ash in, like we do in flotation, we'll have lower tensile strength. If we wash the ash out, like we do in washing, then we'll have higher tensile strength. You can see that ash, inorganic material, cannot hydrogen bond with the cellulose fibers, and for that reason, it interferes with bonding and lowers our tensile strength. And then the last thing is our opacity. Well, our opacity is going to be higher of our resulting pulp. It's going to be higher with flotation and lower with washing. Why do you think that? Well, it goes back to the ash removal. Ash actually gives us a lot of opacity because there's a lot of specific surface area to scatter light with the ash. So for flotation, we're going to have pulp with a higher ash content and higher opacity. For washing, where we've gotten rid of our ash, we're going to have a lower opacity. Okay. And just kind of as a review, we've got two processes that remove ink, small particles, washing and flotation. And they both have their advantages. Sometimes they're used together and sometimes they're used separately. It depends on kind of how old a mill is and how the mill has developed and what product quality is necessary. Flotation, we found out it's a pretty sophisticated process, but when it works really well, and it keeps our yields high. So flotation is a very effective and prominent deinking operation in paper recycling. And that will conclude my lecture on flotation deinking.